Good morning to all. In this video, we will see the continuation of the third lesson. So last class, we saw about the third lesson, that is magnetism and magnetic effects of electric current. We saw the introduction part and also the Earth's magnetic field and its elements. So in this class, we continue that lesson, that is basic properties of magnets. So here some of the basic properties are given. So that first one, magnetic dipole moment. Dipole, do you remember that? We already studied in the first lesson. So what is meant by the dipole? There are two poles are there and separated by the distance. But here we had to consider the bar magnet is also have the two poles, that is north and south pole. So that is considered as a each term as a QM. And the center part is O. So from that center part, the distance can be separated L and L. So OS, ON is separated as a distance of LL, totally 2L. So that is the distance T. So here the direction of the magnetic movement is from north pole to south pole. That is the important thing that can be denoted as a blue color arrow symbol, that is arrow line. So that is called the dipole. So remember that the magnetic dipole moment is defined as the product of its pole strength and magnetic length. So we already studied dipole P is equal to one of the charge into, that is the distance, total distance. Here also the dipole is denoted as the letter PM. PM suffix magnetic moment. So PM is equal to QM, any one of the pole strength, QM into the total distance D. D is equal to 2L. D is equal to 2L. That can be, the direction can be taken from south pole to north pole. So this is the first property of magnet. And second one, magnetic field. The second one, magnetic field. So what is meant by magnetic field? Generally, the field refers the area, that is region or space or area. So you have to play it like that. So when you take a bar magnet, so you have to fill with the iron fillings. So it can be stick in the poles of the bar magnet, and also you keenly observe that there are a lot of lines, that is small lines or there like that. So that is called the magnetic field. Around that field, so the limitations is there. So some area only cover that the magnetic lines of forces. So that area only called the magnetic field. Or the magnetic field is the region that which it's influenced by the, that is we have to kept by another magnet, that region. So it can be limited to attraction or repulsion takes place. So apart from that, we have to increase the distance, the magnetic field can be, we are not felt that field. So up to that region only we have to consider it as a magnetic field. So that field can be denoted as the letter B. So B is equal to, so you very well about that electric field, E is equal to force by charge. So here also magnetic field B is equal to force divided by any one of the pole strength. So F vector by QM. So the magnetic field is a region around every magnet kept by the another magnet in that region. So B is equal to F by QM. So this is the expression for magnetic field. So B is the magnetic field and F is the force that can be influenced by the other magnet divided by any one of the pole strength. So this is called magnetic field. Next one, types of magnets. The magnets can be classified into the two types, that is artificial and natural one. So for the natural, the examples are iron, cobalt, nickel, etc. that are considered as a natural magnet, that are very less strength and very less attractive power like that. And also very weak of that magnetic force of attractions, and also shapes are irregular, so that are considered as the natural magnets. And also the artificial one we have to made, that can be, we have made for the desired shape and also for strengthen that magnetic fields, and it can be form a lot of shape we have to given. So for example, for rectangular, that is a bar magnet, and also for cylindrical, that is a ring magnet and horseshoe magnet. So these are all the shapes of the artificial magnets that are very strength because of force of attraction. So that is called the artificial magnets at which we made them. Next, some of the properties of magnets are, so in your book they are given, so you have to go through the properties of magnet, that is one of the 3 mark or 2 marks. So here this picture represents when the bar magnet is suspended freely, so it always comes and rests in the position of north and south direction. So using the compass you also testing that, so it can be always suspended in the direction of north and south. That is the one of the property. And another one is the magnetic field lines. We have to using that bar magnet that can be fixed in a drawing sheet, and using the compass we have to draw the magnetic field lines also. So from north to south we have to point out the field lines and join the all the points, and that you will get the magnetic field lines. This is one of the practical part in 10th standard. So and also magnetic length of the bar magnet. So here we represents the total length of the bar magnet is called the magnetic length of the bar magnet. Generally we refer as 2L or is equal to D. And also when the magnet is cut into pieces, so it will forms the 2 poles. So not in a dipole, it always in the, sorry, not in a monopole, it always in the dipole. So here one of the bar magnet is there, so we have to cut the equal half of that. So what happened, there are 2 pieces we can get. So that 2 pieces have each one of them have a 2 poles and separated by the distance. So that is the main property of the magnet. So next one, magnetic field lines. So magnetic field lines or the continuous, this lines or shows the magnetic field lines. This is a continuous closed curves line. So the direction of the magnetic field lines is from north pole to south pole. So the arrow symbol itself shows that. And also, so the south pole to north pole inside the magnet. So this is the magnetic field lines. There are number of lines are produced around the magnet. Up to that area only, that is referred as a magnetic field. So next property, the direction of magnetic field at any point on a curve is drawn by the tangent to the magnetic lines of force that point. That is tangent of that values. So the curve line is tangent to that magnetic line of force. So third one, these magnetic lines never intersect to each other. They do not touch. That is not a possible way. So that can be separated. Each and every line can be separated, never intersect to each other. So and also fourth one, so the closeness of the field produces the strengthen, and the spacious part is considered as the weakness of the magnetic lines of force. The closest region produced only the edges of the 2 poles, and the weakest part is produced around the, when the distance increases, the strength is also decreases. So that is the fourth property. Next one, magnetic flux. So what is meant by magnetic flux? Do you remember that electric flux? So electric field lines can occupy a particular area, that is called as a electric flux, that we already studied in first lesson. So the same procedure here also mentioned, that is the magnetic flux. So here the two parallel plates gives a strong, that is uniform magnetic field here. So in this field we referred any area, that is A. So the blue color area is referred as a A. So that area, so that is called the magnetic flux, the number of magnetic field lines crossing per unit area. So how many number of lines can be passing through that area? So that is called as magnetic flux. So magnetic flux is the number of field lines that can be covered a certain area is called a magnetic flux. That is denoted as a letter psi b. Psi b. Mathematically it can be expressed as so b dot a vector. So here B vector is a magnetic flux of the surface of area A vector in the uniform magnetic field. So psi B, that is magnetic flux, is denoted as psi. Psi B is equal to B vector dot A vector. So it is a dot product. So finally we will get BA cos theta. So here theta is the angle between B and A as shown in the figure. So here the angle is produced. So here the magnetic field lines, that is B, and also the area represents the A. The angle between the two value is called the theta value. So finally the expression of the magnetic flux is psi B is equal to B dot A vector is equal to AB cos theta. So this is the value of magnetic flux. Then the special cases is also there. In this special cases, B vector is normal to the surface, then theta is equal to 0. Then substitute that theta value in the equation, general equation. So magnetic flux phi B is equal to BA, that is maximum. So when the area is normal to the magnetic field, the magnetic flux is maximum. Then second case, B is parallel to the surface, that is theta is equal to 90 degree. You substitute that, cos 90 value is 0. So the magnetic flux is also 0. Full value is 0. That is minimum value. Suppose the magnetic field is not uniform over the surface. The equation can be written as, so not in uniform over the surface. So phi is equal to integration of B vector dot dA vector, that is change in area. So it's an irregular part. Then magnetic flux is one of the scalar quantity. So it is denoted as a symbol, so psi, and also the SI unit of magnetic flux is Weber. And also this is the dimensional formula for that. So 1 Weber is equal to 10 power 8 Maxwell's. And also magnetic flux density. So what is that density? The number of lines crossing per unit area is more than the magnetic flux density is high, or the number of magnetic field lines or crossing over the area is low, the magnetic flux density is low. So that can be referred as magnetic flux density is denoted as the number of magnetic field lines crossing per unit area, that is also kept in normal to the direction of the lines of force. So it is called the magnetic flux density, and its unit is Weber per meter square or Tesla. So the last one is uniform magnetic field and non-uniform magnetic field. So uniform magnetic field, so here they arranged as a uniform magnetic field. So all have the same magnitude and in a same direction is considered as a uniform magnetic field. So non-uniform magnetic field is so here they are equally spaced. The magnitude is also same for all and it goes in the same direction. Same magnitude, same direction. So here non-uniform magnetic field. So here the A picture shows the magnitude is different. So and also it goes in the same direction. But B picture, so it is curved line and C is a irregular lines. These are all considered as a non-uniform magnetic fields. So we will continue in the next class.